We move on to heat engines and the second law of thermodynamics. We have cyclic process, and also we have Carnot engines to discuss when we talk about the second law of thermodynamics. In a typical cyclic process, energy is transferred from the environment to the system. So the system takes heat, and the system performs work. Part of this heat is used to do work, and the other part is expelled to the surrounding, which is at a lower temperature from the original heat source. For example, in our cars, by burning gasoline in the engine, that is the source of the heat. Part of that heat is used to do mechanical energy to move the car, and the remaining part is expelled through the exhaust to the surrounding, which is the atmosphere, which is at lower temperature than the temperature of the engine. That is a typical system. That is a cycle that repeats over and over again. So we have a hot reservoir at temperature TH, where the system takes quantity of heat QH. The engine performs work. For the car engine, it does mechanical motion. And there is an amount of energy being expelled to the surrounding. We call it the cold reservoir. So we deal with a hot reservoir and a cold reservoir. The temperature for the cold reservoir is less than the temperature for the hot reservoir always. The change in the internal energy for this cyclic process is 0. Therefore, Q equals minus W. And the Q here is the net difference between QH and QC. We are interested in the net heat energy. This is the one that is related to the work done by the engine. So the difference between QH and QC, Q net, is equal to the work done by the engine. Here, this area represents the cycle. So the area in the PV diagram is equal to the work done by the engine. The efficiency of the heat engine is equal to the work done by engine divided by the QH. If you go back, so this is the output, this is the output, this is the input, this is the waste. So the efficiency equals the output energy divided by the input energy. This is how we define the efficiency. And the work done by the engine is the difference between QH minus QC. So here you have QH minus QC divided by QH. Simplify. This is equal to 1 minus QC over QH. QC is always less than QH, so this is a fraction. 1 minus fraction is another fraction. So this tells us that the efficiency will always be a fraction. It will never be 1. It will always be smaller than 1. This is called the thermal efficiency of the heat engine. The heat pump is also a heat engine, but it operates in a different way. Like inside the refrigerator, there is a heat pump. There, the heat pump takes the energy from the cold reservoir and dump that energy to the hot reservoir. Inside the refrigerator, it's cold. It takes energy from the cold reservoir and dump it to the surrounding, which is the hot reservoir. Of course, this will never happen spontaneously. This will never happen by itself. In order for this to happen, we need to provide mechanical energy, mechanical work an outside source. Okay, so the motor of the refrigerator here uses electric energy to takes the energy from the cold reservoir at temperature Tc and dump it to the hot reservoir at temperature Th. So as you can see here, this engine will never work by itself except if you provide the needed work from this external source. The same model applies to air conditioning also, the ACs. There also the same thing. We provide work from the electric outlet such that we are able to take from the cold reservoir to dump in the hot reservoir. So this is an example of the heat pump, the refrigerator. We see how this motor takes electricity from the power outlet and exerts work on the gas such that it's able to move heat energy from the cold reservoir inside and emit it to the surrounding, which is at a higher temperature. The efficiency for the cooling mode is QC divided by W. The efficiency for the heating mode for the heat pump is QH divided by W. So as we see, the efficiency is always less than 1. The efficiency will never be equal to 1. This is the difference between the second law and the first law of thermodynamics. First law of thermodynamics speaks about energy conservation. That whatever energy given to the system, it will appear in the form of work or change in the internal energy. Energy is conserved. But here, the second law of thermodynamics tells us that no matter what we do, we cannot get a work equals to the input energy QH. There will always be waste energy released to the environment. So this is a constraint on the first law of thermodynamics. Okay? So the first law says we cannot get a greater amount of energy out of a cyclic process than we put in. That's energy conservation. But the second law says we cannot break even. Okay? Cannot break even because always the energy output will be less than the energy input. Another topic that we need to learn about is the reversible and the irreversible process. By a reversible process, we mean to take a system from one state to another state and bring it back to the original state. Irreversible, this means that it is not possible to return the system to its original state. Consider, for example, the car engine that we were talking about. In the car engine, part of the heat energy used to do mechanical work to move the car, and the other part is expelled to the environment from the exhaust. Can you think of a way to collect the energy released to the environment from the exhaust and bring it back to the system? Of course, this is impossible. So this process is irreversible. We cannot bring the energy released to the environment again to the system. We cannot go back to the original state. This is irreversible. Another example, smoke that is going in the air from a chimney, for example. Can we return this smoke back to the previous state? The answer, of course, again, is no. So most of the processes that occur around us are irreversible processes. You cannot reverse them. A reversible process is an ideal process. Okay? it is an ideal process. In real life, most processes that occur in thermodynamics are irreversible. You cannot reverse them. An engineer in France named Carnot proposed a model in the 19th century for an engine which now it's called after his name, Carnot engine. This is an ideal engine. This sets the limit, the upper limit for the efficiency of any heat engine. And it allows for reversible processes. As I said, this is theoretical engine, theoretical model. So here we have 4 phases. We have this state, the gas expands from A to B. This state, the gas expands adiabatically from B to C. The first one was isothermally. The third process, the gas compresses isothermally from state C to state D. And the fourth process, the gas goes back from D to A. So this is a reversible process. It does that adiabatically here. These 4 states are outlined in more details here so that we understand this Carnot engine. So this is the first process. The gas expands isothermally, gaining energy from the hot reservoir, and it goes from state A to state B. Then in the second segment of the cycle, the gas expands adiabatically and goes from B to C. Adiabatically means Q is 0. Then in the third segment, it goes from C to D. The gas compresses isothermally, exhausting thermal energy to the cold reservoir. The temperature for the cold reservoir is less than the temperature for the hot reservoir. And in the fourth segment, the gas compresses adiabatically, goes again from D to A. Adiabatically means Q is 0. These are the 4 processes from A to B, from B to C, from C to D, and from D to A. So B to C, this is gas expansion adiabatically. From D to A, this is gas compression adiabatically. From A to B, this is isothermal process. And from C to D, this is isothermal process. So here, the system takes quantity of heat from the hot reservoir, and here it releases quantity of heat to the cold reservoir. The ratio between QC and QH is the same as the ratio between TC and TH. So the efficiency that we wrote earlier as 1 minus QC over QH for the Carnot engine, because QC over QH is equal to TC over TH, then we can write the efficiency for a Carnot engine as 1 minus TC over TH. As you can see here, efficiency will always be a fraction. It will never be equal to 1. So all Carnot engines operating reversibly between the same 2 temperatures have the same efficiency. Because you are dealing with 2 temperatures, since the 2 temperatures are fixed, then the efficiency will be fixed, regardless of what engine you are talking about. Then all real engines operate irreversibly. This is the difference between the theoretical engine, Carnot engine, and the real engines around us, which operate irreversibly, which means you cannot go back to the original state of the system. And the efficiency here would be less than the efficiency for a Carnot engine. So a Carnot engine sets an upper limit for the efficiency of any heat engine. 3 engines operate between reservoirs separated in temperatures by 300 Kelvin. The reservoir temperatures are as follows. For engine A, TH 1000 TC 700 Kelvin. For engine B, TH 800 Kelvin and TC 500 Kelvin. For engine C, TH is 600 K and TC is 300 Kelvin. Rank the engines in order of their theoretically possible efficiency from highest to lowest. To solve this problem, you need to use this equation for the efficiency, because this is the highest possible efficiency. We know TC, we know TH for these 3 engines. So when you do the math using the efficiency equation, you get this result: CBA. CBA. This is more efficient than B. B is more efficient than A.